Wind energy. Wind energy has become one of the most important sources of renewable energy. One of the important economic benefits of wind power is that it reduces the exposure of economies to fuel price volatility. Many renewable energy sources, like wind and solar power, are dependent on the environment. Wind energy specifically is dependent on wind speed and wind direction. Due to the unpredictability of weather, accurate wind forecasts are crucial in providing useful information for energy market trading, reducing imbalances in charges and penalties by ensuring the energy demand is always met. The three main players in energy market trading are grid operators, energy producers, and energy traders. By playing the role of energy traders, our goal was to get an hourly T plus 18-hour energy forecast, and our objective was to maximize profits for the client using energy production forecasting and the given trading algorithm. Moving on to our dataset, we were provided data from 8 wind farms in the Ile-de-France region by TerraWeather. We used this data to create our chosen full dataset consisting of average wind speed across all 8 farms in meters per second for every hour from 1st January 2017 midnight to 18 July 2020 noon, for a total of 31,068 hours. We extracted the average speed of the wind forecast as we are aiming to predict the amount of wind speed across the whole region. Moving on to model building. The dataset was pre-processed before being used to train the neural network model. We started by obtaining the relevant information about the dataset, including mean, median, standard deviation, maximum, and minimum. We then continued by normalizing the dataset by using the formula as shown. Normalization is done to ensure that the attributes are grouped together in such a way that there is no redundancy, or at least controlled redundancy. The features we used are mean and standard deviation of energy production of the past 4 hours and the weather forecast. We tried to add momentum and force in our features before final deployment. However, since it didn't help, we removed it. We tried different configurations, and these are the results obtained. After several attempts, we concluded that the best configuration had an input size of 4, a neural network size of 16, using the Adam solver. This configuration showed the best test loss of 0.347, which beat the persistence benchmark of 0.44. The lag plots show that both the training and test peaks appear at lag 0 and then at 18. And the scatter plots display a linear relationship, indicating that the learning was successful and that our model is predicting some inputs. As the test scatter plot is not too scattered, this also suggests that the model is not overfitted. In summary, our group's neural network model performed well with relatively small test losses and produced good predictions that help the wind energy producers make profits. While our model may not be the best, we believe that it produced acceptable predictions and performed fairly well without incurring huge penalties or losses. Thank you.